Hello and welcome to this Bits of Q Advanced C++ tutorial. My name is Quirijn, and in this episode we'll be talking about Move Semantics. Move Semantics were introduced with C++11, so they've been around for more than a decade now. Yet they still tend to cause quite a lot of confusion. In this episode I want to explain what Move Semantics are, what their benefits are, and how you can use them. We'll start our story with this simple article class. It represents some kind of article, say a page of Wikipedia or something in a magazine. But what's important for us is that it encapsulates a big string, mcontent. Now if you have to operate on a lot of these articles, say you're trying to process the millions of articles on Wikipedia, then you want to make sure that these operations are efficient. And in particular, you do not want to make unnecessary copies of this big string. So let's see how a typical snippet of code might interact with this article class and when copies are made in this interaction. We'll look at the snippet on the left. And for the sake of this little analysis, we're going to assume that we're still using C+03, so we'll be ignoring Move Semantics. And next to that, we'll also ignore any compiler optimizations that might try to eliminate copies. On the first line, we are constructing our article based on whatever is returned from read content. Now the string is going to be accepted by reference to const, so we're still good here. But then it has to be copied into this local mcontent member. So that's our first copy. Somewhere further into our program, we might pass our article to a reformat function. This reformat then returns some new content, which we'll assign to a local variable, which is copy number 2. At that point, we actually want to set this content, so we pass it to the setContent member function that accepts this content by reference to const, so we're still good. But then again, we have to make a copy to assign it to our local mcontent. So in total, 3 lines of interaction with this article class and 3 copies. But if you look at it carefully, a lot of these copies are actually not needed. For example, on the first line where we're constructing our article, the thing that's being returned from read content is not going to be used anywhere else. So why are we carefully trying to preserve the original and creating a copy here? Would it not make more sense to just directly move whatever is returned from read content into our mcontent member? We see a similar thing happening on the second line. The string that is returned from reformat is not going to be used anywhere else. So why are we trying to copy it? Why not just directly move it into new content? For the third line, we have to be a bit more careful. Because say this new content that we're passing into our article is still used somewhere else. Maybe somewhere further down the line we do some other operation on it. In that case, it makes sense to make a copy here because we want to leave the original new content variable intact. So some copies are necessary, whereas others are not. In this case, only one copy is actually necessary. And this is what Move Semantics are all about, eliminating unnecessary copies. So to explain what a move actually is, let's look at these 2 strings. We have a string A and a string B, and since strings manage some dynamically allocated memory, they both contain a pointer to their data A and data B. Now if I copy string A into string B, what's going to happen is all the data of A is being read and it's written to the string B. Depending on whether there was more data in A than there was in B, it might need to allocate a new chunk of memory before it starts doing this copy. All in all, a very expensive operation. When we do a move on the other hand, we're actually just assigning A's data to be owned by string B. So that's something to keep in mind. A move does not actually move data, it only moves ownership. And that's a good thing, because if we were to actually move the data from A into a different spot in memory, it would still become a really expensive operation. Another thing to keep in mind is that since we're now moving this ownership of A's data, String A no longer owns any data. In other words, a move is destructive. Now, luckily for us, the compiler actually takes care of moves by itself. It will try to identify the cases where a bit of data is not used anymore, when it's something that's temporary, that's expiring, and in that case, it will do a move instead of a copy. Of course, the compiler is not omniscient, so we need to tell it how to do a move for new data types. And of course, there are going to be cases where we as programmers know that a certain variable will not be used anymore, but the compiler doesn't know this, so we might need to help it a bit. In the rest of the presentation, I'll explain how both of these things work. But first we should talk about when the compiler actually decides to do a move. And to do that, I first want to take you all the way back to 1972, when the C language was invented. Looking at this simple assignment statement in C, the inventor of the language needed to decide when an assignment was valid. Clearly, one of the main rules is that the type on the left hand and the right hand of an assignment need to be compatible. In this case, both for and a are of type int, so we're good there. But this is not everything, because for example, the statement for equals a is not valid, so there's more involved than just types. To clearly define when an assignment is valid, the concepts of lvalues and rvalues are introduced. An lvalue is something that occupies storage in memory. An rvalue, on the other hand, does not occupy storage. It's something that's temporary. It might, for a brief moment, exist in some register, but it's never really in memory. So looking at our snippet, a is a variable that is associated with some piece of data in memory, and hence is an lvalue. 4, on the other hand, is an rvalue. Now the rule for when an assignment is valid is that the thing on the left side needs to be an lvalue. In other words, rvalues can only appear on the right side. Now as the years progressed and the C language improved, later on we got C++, and there we also went through several versions, this distinction between lvalues and rvalues became a bit more nuanced. Lvalues might not always occupy storage when certain optimizations are involved, whereas in certain cases rvalues do need to occupy a bit of storage. But looking at it from a semantics point of view, lvalues at least behave as if they occupy storage, and rvalues behave as if they do not occupy storage. As an example, a compiler might optimize out the storage usage of an lvalue, but it will still allow you to take the address of an lvalue. So you can still interact with this lvalue as if it has some actual storage. If you're interested in all the little details about how the compiler looks at your data and the different value categories that exist, I'll add a link in the description for some additional information. For the sake of this presentation and for the sake of understanding move semantics, the simple distinction between lvalues and rvalues is sufficient. A nice rule of thumb to keep in mind when trying to identify lvalues and rvalues is that an lvalue has a name, whereas an rvalue does not have a name. So looking at another simple example, here clearly all our a's and b's are lvalues, they have names, they occupy some storage in memory. The 2 we see here is again an rvalue, no storage is associated with it and it does not have a name. But then there's also the result of this expression a plus b. Even though a and b themselves are lvalues, a plus b is an rvalue. The result of this addition is something temporary that does not have a name and does not occupy storage. Similarly, the thing that's returned from foo is again an rvalue. Now one of the things that C++ introduced was the concept of references. The normal references, as you're used to using them, are actually references to lvalues. For example, in this case, b is a reference to the lvalue a. In other words, it's an lvalue reference. Now a reference type which you might not have seen before is the rvalue reference. it uses the double ampersand syntax and it can only bind to an rvalue. If I try to create an rvalue reference D and then bind it to A, I'll get an error. Something like cannot bind rvalue reference of type int ampersand ampersand to lvalue reference of type int. In other words, this D cannot be bound to A. The same holds true the other way around. If I have an lvalue reference E, I cannot bind it to an rvalue reference. In that case, I might get an error like this. Cannot bind non-const lvalue reference of type int ref to an rvalue reference of type int. So our non-const lvalue reference is the E in this case, and the rvalue of type int is what's returned by foo. Now the non-const in this error message already gives a hint at a special case, because indeed an lvalue reference to const, like our f here, can bind to both lvalues and rvalues. So what do all these lvalues and rvalues have to do with moves? Well, the compiler will attempt to move some data if either we're dealing with an assignment and the right hand side is an rvalue, in which case it will perform a so-called move assignment, or if we are doing construction of an object and we're trying to construct this instance from an rvalue, it will do a move construction. And similar to how we can define copy assignment and copy construction operations for our classes and other types, we can also define move assignment and move construction operations. So looking back at our article class, how can we make sure that we can both copy and move our article? Well, the first thing to keep in mind is the rule of zero. And the rule of zero says that as long as none of the destructor, the copy operations, or the move operations have been defined, then the compiler will just try to generate default implementations for these operations. So in this case, we don't have to do anything to make our article copyable and movable. This rule is also known as the rule of 5, which basically goes like, if you define one of these 5, you should define all of them. And its predecessor before we got Move Semantics was called the rule of 3, which was only about the destructor and the copy operations. Let's say we have a class where we do need to define a destructor. For example, we're writing our own string class, so we need to manage our own memory. And to ensure we don't leak any memory, we have a free in our destructor. In that case, we'll have to write our copy operations. So as you might remember, the copy operations take the auto string from which they're copying as a reference to const. The move operations look very similar, except that they take the auto string from which they're moving as an rvalue reference. Next to that, I also added the noExcept keyword here. This keyword is not necessary to define your move operations, but it's highly recommended to make your move operations noExcept if at all possible. The reason for this is that the standard library, as well as many other big libraries out there, such as Boost, will often try to optimize their algorithms in case they are dealing with a data type that's movable, but they tend to only do so when they can be sure that moving the type around does not throw any exceptions. So to make sure that your type is as efficient as possible when used with these kind of algorithms, try to make sure that your move operations do not throw any exceptions, and also mark them as such with the noExcept keyword. So what could such a move operation look like? Let's take the move assignment for example. Whereas the copy operations make deep copies, here we know that this auto string from which we're moving is actually something temporary. It's something that's expiring, so we can freely do destructive actions on this auto string. In particular, we can just take the mcontent pointer of this auto string and use it for our own mcontent. Now, even though the auto string is being moved from, at the end of this move operation there will still be an instance that will still get destroyed at some point. So to prevent this auto string from also trying to erase its content, we will set auto.mcontent to null. This way we prevent a double free. So let's look at move operations in action. We'll go back to our original article class with the snippet of code on the left. I just made one small change here. I added a second setContent operation, one that takes its input by rvalue reference. Now, using our newly obtained knowledge about lvalues and rvalues, I can color code the snippet on the left. And we can again identify where things are being copied and where they are not. So in the first line, we have our construction happening. An rvalue is being returned by read content. Our constructor accepts an lvalue reference to const, and luckily lvalue reference to const can bind to both lvalues and rvalues, so that's why that's all compiled. But even in C+11, there's still a copy happening here, because we're dealing with an lvalue reference and we're copying that into our local mcontent. Now, the second line, something does change with C+11. Reformat returns something temporary, something expiring, an rvalue. So the compiler knows, hey, I can safely execute a move here, and will move whatever is returned by reformat into new content. Then, looking at the setContent operation here, we are passing new content, which is an lvalue. So out of the two overloads, it will choose the topmost one, the one which accepts an lvalue reference to const as input. Now say we will not be using our new content anymore. We as developers know this, but the compiler doesn't know this, so it will still try to make a copy here. If we instead want to make sure that the second setContent overload is chosen, we need to make sure that we pass an rvalue instead of an lvalue. And we can do this with the std_move operation. Now the name of this operation is somewhat misleading, because as we have learned, the compiler is actually one that decides when to do a move or not. This is not something we can implement ourselves. So std_move does not do a move. But what it does do is essentially cast your input to an rvalue reference, which signals to the compiler that this is something temporary and that it can be moved from. In this particular case, however, all that's happening is that it'll go into the other overload, the setContent accepting an rvalue reference. Now, to ensure that setContent actually ends up moving this C into mcontent, we need to do another std_move. And the reason for this is quite simple. Even though the type of C is an rvalue reference, in the scope of this function body in the implementation, C is something that has a name. C is an lvalue, so we again have to use this std_move to turn this into an rvalue and create a situation where the thing that's being returned is something that's expiring, something temporary, and hence the compiler can do this move. So that's something to keep in mind. On the caller side of the setContent, we have an rvalue, but then inside this function, it's just another lvalue. So we again have to turn this into an rvalue if we want to make sure that the compiler actually does its move. As always, the rule of thumb, if it has a name, it's an lvalue. If it does not have a name, it's an rvalue. Now in this case, in both of our setContent overloads, we're only accepting our C parameter with the purpose of later on putting it into mcontent. This means that we can also simplify this code. Instead of having two different overloads, one for our lvalues and one for our rvalues, we can just have a single overload accepting a string by value. Clearly, both an lvalue and an rvalue can be passed to setContent. In the case of an lvalue, the compiler will make a copy. But that was needed anyways, because we need this for our mcontent. And since we move from the C afterwards, there will be no more copies. In the case where an rvalue is passed, such as what happens in our snippet, because of this std_move operation on the left, the compiler will move the result of this move operation into our string C, and then we'll continue to move it on to our mcontent. In other words, no copies. So we now created a single set content that can optimally handle both being passed an lvalue and being passed an rvalue. And we can do a similar thing with the constructor. This one we can also update to just accept our string by value, and then use std_move to move it into rm content. That means that if our article is constructed from an lvalue, that yes, the compiler will copy it to create our local content parameter, but that's exactly what we want, because clearly we cannot destroy the lvalue on the caller side, because it's not something temporary. On the article side, we do a move, so we do not have an extra unnecessary copy. In the case of our snippet again, read content is returning an rvalue, so here the compiler first moves it into the content parameter, and then we continue to move it into mcontent. So in this case, no copies happen at all. So, to summarize, the main idea behind Move Semantics is this whole lvalue and rvalue thing. Lvalues occupy storage and have a name. Rvalues do not have a name, they are temporaries. We use a single ampersand to denote an lvalue reference and a double ampersand to denote an rvalue reference. Lvalue references can only bind to lvalues, rvalue references can only bind to rvalues. The one exception is that an lvalue reference to const can bind to both lvalues and rvalues. The compiler will attempt to move, in the case of assignment when the right-hand side is an rvalue, and then in the case of construction when we are constructing from an rvalue. If we have an lvalue and we as programmers know that we will not be needing it anymore, we can use std_move to cast it into an rvalue, allowing the compiler to move from it or assign it to some rvalue reference. For the compiler to know how to move custom types, we need to define our own move constructors and move assignments. These operations take their input by rvalue reference, and to make sure they can be optimally used in all kinds of algorithms, it's best practice to mark them as no except. That's it for this episode. I hope you enjoyed it and learned something new. If you did, make sure to leave a like and consider subscribing to the channel. See you next time.